This is part 3 of the crude oil and fuels topic in AQA GCSE chemistry. It's a dual and triple award subject. I'm going to recommend you have a go at each activity, pausing the video as you go. In this video, we are going to focus on the combustion of hydrocarbons. So we need to know what the product will be in complete combustion, where there is a steady supply of air. We need to be able to prove what the products of complete combustion are. We're also going to have a look at incomplete combustion, where there is a limited supply of oxygen, and consider what gets made. And finally, we're going to do some combustion analysis calculations. So let's jump straight in with some questions for you to think about. And with this, whenever you are burning something, you are reacting it with oxygen. So if you burn magnesium, you make magnesium oxide. If you burn lithium, you make lithium oxide. With a compound, it's slightly different. Let's break methane down into its elements. So there's carbon and hydrogen, and I appreciate hydrogen exists as H2, but we're dealing with the compound we make when we burn it. Now, if I then think about what I will make if I combust these, if I react them with oxygen, and with a good supply of oxygen, because we're dealing with complete combustion, carbon, it's logical that I'm going to make carbon dioxide. Hydrogen, you might be thinking hydrogen oxide, which it certainly is, but it has a much more common name. We're actually making water. So the products of complete combustion of any hydrocarbon are carbon dioxide and water. And if you remember that burning anything makes its oxide, and remember that if it's a compound, we make the oxide of each individual element, you'll be well on the way to being able to tackle this. So now let's have a look at the equation that goes with it. We are combusting methane, CH4. So my CH4, I am reacting with oxygen. We're remembering that oxygen is a diatomic molecule, and we've just established that we're making CO2 and we're making water. Now, I'm going to go through and balance in a particular order, and I'm going to reinforce this as we go later on. But I'm going to try to balance the carbons first. They're already done. So now let's balance the hydrogens. Well, I've got 4 on the left, so I need 2 H2Os on the right. And I've now got 4 oxygens on the right, so I need 2 O2 on the left. More questions to think about? So there is a big clue in the title here. We're burning hydrocarbon fuels. Burning hydrocarbons, especially those with shorter chains, is a useful process. It transfers lots of energy to the surroundings. What do we call the type of reaction that releases heat energy to the surroundings? And what we're looking for is an exothermic reaction. And if we then think about chemical reactions that take place that will send heat energy out into the surroundings, where we rely on that, we're thinking of fuels. They release heat energy when they are burned. So we've got this box at the bottom that reinforces some of the information that we're talking about. Complete combustion, we need to know that that is when there is a good or ready supply of oxygen. And whenever we completely combust a hydrocarbon, we will always make carbon dioxide and water. Now, there is a way of proving that, and this apparatus will hopefully look familiar to you. Have a look at it, have a think about the questions. So you can see we've got our Bunsen burner burning away. We have a delivery tube going into this U-tube, and it's got some cobalt chloride paper in. It's also trapped in an ice bath. There's then another delivery tube that's bubbling directly into the lime water, and then up here we have got a water pump. This is a very good example of a cross-sectional diagram. You will notice that the delivery tube goes through the bung. It's not stopped by the bung. That's what you would need to aim for. Have a think about the questions. What hydrocarbon is the main fuel used in the Bunsen burner, and what is its chemical formula? So we're looking here at methane. Methane is CH4. We've just looked at the equation for the combustion of that. What would we observe in the U-tube here? And what would that prove has been produced? There's actually 2 ways to answer this. One, you're going to see water vapour that has been produced, that's gone through the delivery tube, will get into the U-tube packed in ice, where it will cool and condense, and we will see liquid water forming. But we've also got here blue cobalt chloride paper, and in the presence of water, blue cobalt chloride paper will turn pink. It's actually the common test for water that you would hopefully remember. Couple more questions about that diagram. So what would you observe in the lime water, and what does it tell us has been produced? Hopefully when you think lime water, you immediately think test for carbon dioxide. We know that carbon dioxide is a product of complete combustion of a hydrocarbon, so we would expect it to turn cloudy. We'd expect it to turn cloudy, proving that the CO2 that has bubbled through and got to the lime water has been formed. And what's the purpose of the water pump? You can see the water pump way down at the end here. And the water pump essentially creates a vacuum, so that will suck the products of combustion through at a much faster rate, so we can find out and investigate what gases have been produced much more quickly. So let's have another look at some equations for the products of combustion and see what you can do with these. So I'm going to do all of these together collectively, and I'm going to come up with a tip that I hope will help with complete combustion equations, and indeed with incomplete combustion equations that we're going to see later. So let's start off by writing out the beginning of the equation. That's the hydrocarbon that we're combusting. We know in each case that we are combusting them in the presence of oxygen. That exists diatomically, so it's O2. We know that it's complete combustion, so because of that, we know what the product will be. So in each case, it will be CO2 and it will be H2O. And you'll notice that we're making H2O gaseous. That's because at high temperatures, you do tend to find it comes off as water vapour. Now, when it comes to the balancing of the equations, I follow what I call the rule of Cho. This is always valid when you are doing equations for the combustion of hydrocarbons. And what that means is you balance in the order of the letters shown. So you balance the carbon, and you can see here C2H6, 2CO2, C3H8, 3CO2, C4H10, 4CO2. Once you've balanced C, you balance the H's. I've got 6 H's, so I need 3 H2O. 8 H's, 4 H2O. 10 H's, 5 H2O. And once you've balanced C and balanced H, you then balance the O. And that's different on each of these here. So you've got to be careful to add up all of the oxygens carefully. In the first instance, I've got 4, 5, 6, 7 oxygens. So I'm going to need 3.5 O2 to balance it. In the second one, I've got 6, 7, 8, 9, 10 oxygens, so that means I need 5 O2. And in the final one, I've got 8 plus another 5, 13 oxygens, which would mean I would need 6.5 O2. So now let's move on and think about incomplete combustion. Have a think about these questions. So, the products of incomplete combustion of a hydrocarbon are very slightly different. Think about it, you have got a limited supply of oxygen, so we're not going to be able to make carbon dioxide with 2 oxygens and water. The actual change is this. We make carbon monoxide, CO, rather than CO2. However, and this is crucial, you will still make water. So, the products of incomplete combustion of a hydrocarbon are carbon monoxide and water. One of these is actually very dangerous to humans. What gas is this? And that is carbon monoxide. Couple more questions to think about here. And the problems we associate with carbon monoxide, it's a toxic gas. It can cause suffocation. What it actually does is bind in your red blood cells in place of oxygen. It stops oxygen getting to the cells in the body. So what's the equation going to look like? We're going to do one example here. Have a go. Methane is CH4, and we're still reacting it with O2. That's how oxygen exists. But this time, we're making carbon monoxide. Remember, we're still making water. I'm then still going to follow the rule of Cho. I'm going to balance my carbon, then my hydrogen, then my oxygen. My carbons are already balanced. My oxygens, I've got 4 on the left, 2 on the right, so I need 2 H2O. That now means that I've got 3 oxygens on the right. I need 1.5 O2 on the left. Now we're going to look at some combustion analysis questions as well. Take the time to pause this, read it, and then watch the walkthrough. And I'm going to show you an alternative method as well that might seem quite familiar if you've been revising the maths topic. So that's the question. Here is a potential way to answer it. We have got the mass of butane. We can find its MR to calculate the number of moles that we have. I can then use the equation where there's a 1:4 ratio to work out how many moles of CO2 there are. And then from there, I can multiply the number of moles by the molecular mass of CO2, and that takes me to the actual mass of carbon dioxide produced. Now, as I say, in the walkthroughs, I'm going to do a different method. So you might want to watch one through and then try the other two. You might just want to give it a go and see if you get to the right answer. So here's the first question. And on this one, we're butane again. We're doing 7.5 kilograms of liquefied butane. So the equation, C4H10, O2, CO2, H2O, rule of Cho, I balance the carbon, then the hydrogen, then the oxygen. It's 4 CO2, 5 H2O, meaning 6.5 O2. The two things that I'm interested in here are C4H10 and 4 CO2. And when you've got a mass of something and you want to know the mass of something else, there's a calculation you've done on this called reacting masses. I'm going to do this as a reacting masses question. There's a table. You put the two species that you are interested in, the one you know about, the one you want to know about. And then you have mass, molecular mass, number of moles, and ratio. Then you simply fill in the data that you have. We have 7,500 grams of butane, 7.5 kilograms, converted to grams. The MR of butane, 4 12s and 10 1s, is 58. To get moles, I do mass divided by molecular mass. There's a whole topic on that with the chemical calculations. But that means we've got 129.3 moles. I then need the mole ratio. I take it direct from the equation. 1 mole of C4H10 makes 4 moles of CO2. So I put my 1:4 ratio in. If 1 mole makes 4 moles, 129.3 makes 517.2. 4 times the amount. I then find the MR for carbon dioxide, 44, and I've now got the N and the MR that I can multiply to find the mass. 22,759, convert that to kilograms, 22.8 kilograms. Here's another one for you to try. So the equation, we're doing propane, we're making carbon dioxide and water, this is complete combustion once again, and balancing it, we get 3 CO2, 4 H2O, and we need 5 O2 to do it. So I'm going to draw my table out again. I've got my mass, molecular mass, moles, ratio. I'm interested in propane and carbon dioxide, so they are the two that I put into my table. This time, my mass is 10,000 grams, 10 kilograms converted to grams. The MR of propane is 3 times 12 plus 8, 44. I can then use M and MR to find my number of moles. M over MR, we get 227.3. I go to the equation for my mole ratio. 1 mole of propane makes 3 moles of CO2. That's a 1:3 ratio. And if I know it's a 1:3 ratio, that means if 1 mole makes 3 moles, 227.3 makes 681.81. Now, a slightly odd situation here because the MR of carbon dioxide is the same as the MR of propane. It's 44. So when you multiply those two together, we get 30,000 grams or 30 kilograms. Final one to take a look at. We have the equation again, methane reacting with oxygen to make CO2 and H2O. I've added the balancing in, and then I draw out my table. I'm interested in methane and carbon dioxide. I have my mass, molecular mass, moles, and ratio. I've got a kilogram, so that's 1,000 grams of methane. The MR of methane is 16, carbon is 12, hydrogen 4 of them at 1 each. And 1000 over 16 gives 62.5. In this case, the mole ratio is 1 to 1. 1 mole of methane makes 1 mole of CO2. And from there, I can say that if 1 mole makes 1 mole, 62.5 moles makes 62.5 moles. I can then find my MR for carbon dioxide, which is 44, and I can multiply these two together to take me to the correct final answer, 2,750 grams, which is 2.75 kilograms. That takes us to the end of this video. Thank you for listening, and goodbye.